Okay, good. Okay, so I hope that you are so enjoying my class, hopefully, huh? Okay, so guys, so let's continue because I want to finish the growth stability criteria by the next week, and then I'm gonna send midterm and on your spring break. Okay, so let me finish topics before sending the midterm. Hmm? And that's for that. I have to teach you about. I'm done with the dominant poles and the body and this kind of everything, highest order system to second order system, everything. So I'm going to teach you about the type of system. Type of system. Okay. And taking back to the super important example of the pendulum that now I know that you love it in all my classes. And I told you from the dynamics, if you had dynamics with me until today, in the vibration in ME432, in the robotics, this is super important because I'm going to back to this example several times. If you remember that you apply a torque here, that's right, to control this pendulum, you know that theta over tau is, for example, is 1 over, say, s squared plus omega n squared. We derived this together at the beginning of this course. And now you know that you have two poles located on the imaginary axis, means your system is marginally stable. And the poles of the system is plus minus I omega n. So it means that you're on the imaginary axis and you're marginally stable. And this is open loop transfer function G. This is what I want to remind you now. Being said, if you go and I taught you in the coding and in the Simulink, this is desirable angle, okay, and then going to the unity feedback, right, and then we're gonna put this tau here as, or U, generally speaking, as a controller. Then it goes to the open loop transfer function of 1 over s squared, if you remember, omega n squared. This gives you the real angle is being compared in the presence of the ideal sensor unity feedback, then this gives you E, right? And this is the G. So open loop transfer function. So now I taught you like the fourth order system by two spring and mass damper in the previous classes. Even you can sixth order system, 10th order system, 100th order system. Generally speaking, if your G open loop transfer function is this, like Bm s to the power of m plus Bm minus 1 s to the power of m minus 1 plus finally B naught over an s to the power of n plus an minus 1 s to the power of n minus 1 and coming here and the a naught. And now you tell me, because I taught you how many poles we have here. How many poles we have here? Huh? How many poles? This is nth order equation, Sn, like as the high school. How many poles we have here? Huh? Yes, n poles we have. That's right. This is from high school. Because you have n roots. And how many zeros we have here? How many zeros? Huh? How many zeros? Yes. M zeros we have here. Or the open loop transfer function of any system I'm talking about. You can say, I don't know, 5 tangle water in series, or you can say 7 degree of freedom robot I have in my lab, Baxter, that is a 14th order system. Baxter is if you linearize, which is not possible because that's a nonlinear and you cannot linearize it. But this 7th order system means that you have 14 orders, so you have 14 poles for the Baxter in my robotic lab. Okay. So now you can rewrite this. Now you have m poles. You can say g of s open loop transfer function can be written as s plus z1 s, you know, from high school, and we did here for the different problem, z2 and s plus zm, okay, because you have m zeros, divided by s plus p1, s plus p2 poles, and s plus pn. Right, everyone? Record, right? Yeah. Okay. You got it. Can I go to next page, everybody? Yeah. No, I'm gonna send a midterm when you are at your break, because it's gonna be a very challenging question. One question, you have to spend many days on that. Okay? Two. Yes. Yes. Okay. 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 You got it. Can I go to next page? Okay. So now you can write this by factoring out z1, z2, zm, p1, p2, pn from here. So you're gonna have z1, z2, z3, zm, and now you're gonna have 1 over z1 s plus 1, 1 over z2 s plus 1, see, and 1 over zm s plus 1. The same for the poles. You can say p1, p2, pn, 1 over p1s plus 1, 1 over p2s plus 1, 1 over pn s plus 1. Being said, I'm just defining, playing with the parameters, naming them. I'm saying I'm gonna name this as the gain k, because these are numbers, that's right, k, and I name this as t1 s plus 1, t2 s plus 1, and tm s plus 1. Okay, you got it? Now I'll name this t prime 1, t prime 1 s plus 1. Just bear with me, guys, hold on. Okay, and t prime s, t prime 2s plus 1, and t prime n, because you have m poles, plus 1. This is the general statement of open loop transfer function for any order system. Because the two mass spring damper that we solved in the other class, it was fourth order system. You had 4 poles. N was 4, and you have 2 zeros, remember? So N was 2. Remember? But this is generally speaking. We're expanding to any nth order system and nth order zeros. Open loop transfer function. Now this helps us that we introduce type of a system. Type of a system. The first type is type 0 system. And guys, I can compact this before going there as K from high school. And you can, this is notation for multiplying big pi, that's right, from say I from let me write it here, guys, because it's gonna, oh my god. Oh. I have to open a new blank presentation. So I can write here G, I'm moving that, okay, as K multiplying big pi from I from 1 to M T I S plus 1. See? And divided by pi means multiplying J from Y to N T prime J S plus 1. I just compacted the, generally speaking, the open loop transfer function of any system like this. Can be 7th order robot, can be 25 order robot, can be whatever. Okay? You got it? Being said, now I define type of the system, as I said, type of systems in control, linear control domain. The first is type 0. Type 0 system means that there is no integrator. I'm writing down here with another color, you write. The open loop transfer function, the open loop transfer function has no integrator term. Guys, I taught you this million times. What's integration in the Laplace domain? You tell me. Huh? What's integrator? Laplace of integrator, what is that? You have in your notes. Is 1 over S, PID. I is for integrator, 1 over S. So your G is like this. Is exactly like this. I from 1 to M, TIS plus 1. J from 1 to N, T prime JS plus 1. I'm changing the color to show it like here. S, N. N is type of the system. When N is 0, S to the power of the 0 is 1. So you have no integrator. That's right. So when you do that, means the N is 0, type 0, N is 1, N is 0 here. Type 0 system. Your open loop transfer function has no integrator. Has no integrator. N is 0. 2. Type 1 system. As its name implies, your N is 1. Your system has integrator. One integrating open loop transfer function is K I from Y to M TIS plus 1 J from 1 to N T prime JS plus 1, and here you have S. You have one integrator. See, I'm showing 1 over S. You have integrator. Means that your system has one I controller intrinsically inside itself. Interesting, right? And when I teach you PID controller, what's the function of I, as already mentioned, but mathematically, I mean, you're going to see it's a good system that has one integrator inside, one I controller inside. This is type 1 systems. You got it? And now, can I go to the next page? Yep. Then, finally, 3. Type 2 systems. As its name implies, N is 2. You have 2 integrator in open loop transfer function. Can you please mute your speaker, guys? Please. So it is S2. We have two integrator. 1 over S, 1 over S. And you're gonna tell me, Payman, what's the point of these? This is gonna exactly help me to teach you the next topic. Error constants. Before going to Ross-Hewitts. Error constant, the next topic. In linear control domain, error constants. Because accept from me now, I'm teaching, but now in detail, but I'm telling you the I controller, I'm gonna show it, okay? I controller function is, as I told you once, is to remove steady state error signal in the system. One of the function of the I control is that. So when you see that your system has two controller, I controller, or one controller, means that your system is good by itself. If you have such a system, you don't need to add another I. You only have to design PD or P controller for that. You get it? I'm going to show it next time. Error constants. What's that? The next topic. Static, the first topic. Position, this is the name. I'm going to define right now. Static position error constant. Static position error constant. Remember, guys, from day one I told you we have 5 inputs to the system. Impulse, unit step, ramp, and parabolic. And we know that in the Laplace domain, they're going to have these transfer functions. Now you're expert of that. Right? So, if I apply the first one, impulse, case 1, okay, you know that ESS, as I told you, final value theory, gonna be limit of S x of S, you know it, plus 1 over G. So when I said case 1 is that your x of S is 1 over S, is unit step. If you put that here, it's gonna be S. Now I'm speaking generally, not for second order, first order, third order, 10th order. I'm speaking generally now for any system. 1 plus G of S. When S goes to 0. When S goes to 0. This S with this S goes to Denver. You get that ESS is a limit of 1 over 1 plus G of S when S goes to 0. Guys, you see that I'm hesitating because I have no notes. I'm teaching from my mind. I have to refresh my mind from previous, from last year. Okay. So if you put S0, you're gonna get this 1 plus G at 0. The name of this we name as static position error constant, and we're gonna name as this 1 plus KP. Kp is static. I'm gonna tell you why we name it static. Why we name it position. Error, it is error constant. Kp, we name it as that. Just bear with me. It has a logic. It's not by accident. Error constant. Second, I'm gonna back to this. Okay, now I'm done. Not yet. Second, B. Static velocity error constant. Static velocity error constant. We're gonna use this when I teach you lead lag controller at the end of the semester. Lead lag controller. When I teach you this, I'm gonna use this. So ESS as again is limit of s x of s 1 plus g. With g, this g. Now we formulated for any system based on type of system. This g. Okay. Now for static position error constant, our input was unit step. Now if I apply the ramp as input, so x of s is gonna be 1 over s squared. I'm gonna just implement here. Gonna be a limit of, obviously s goes to 0, final value theory. S 1 over s squared, 1 plus g of s. I'm putting s because, yeah, it's s. Changing the color, this one of these goes to New York, and you can take it down like this, the other s. S plus s g of s when s goes to 0. From here, steady state by the input of the ramp. If you put S0 here, look at here guys, it's gonna be 0. Now SG of 0, we name this as static velocity error constant. Bear with me, it had the reason. So we name it as 1 over KV. KV is velocity for velocity. This P is for position. Okay. So we define KV as SG. These are definitions. We're gonna use this in designing lead lag controller after PID. I didn't write it here, so I'm writing here. KP is open loop transfer function at S0. Right? Yeah. Now C. Now C. Static acceleration error constant. In the previous cases, we used the unit step as input, ramp as input. Now I'm using parabolic as input. So now we know changing the color. ESS again is a limit of s x of s again, final value 3 that I taught you. G of s when s goes to 0. Difference is that x of s is the parabolic 1 over s cubed. Now you know it. Putting here 1 over s cubed 1 plus g of s when s goes to 0. This with one of these three goes to, you name it, San Francisco, and you get s squared plus s squared g of s. Sorry, g of s. Let me fix this, guys. G of s. S goes to 0. If you put that again 0 here, so you get ESS gonna be 1 over s squared g at 0. S is 0. We name this as K, Ka. A is for acceleration term. So gonna be 1 over Ka static acceleration, A error constant, Ka. Okay, these are definitions. So Ka we are defining as s squared g 0. You got it, everyone? Now you're gonna tell me, Payman, why you name as position velocity, acceleration? Why did this backs to your dynamics combined with control, ME220? Simply speaking, I said K position, I'm just summarizing, is G open loop transfer function at S0. I said KV is S G of S. And I said Ka is S squared G of S. Now you only have to know these, not the process I drive. Okay, guys, let me take you back to your dynamic course, ME220. This is displacement in ME220 chapter 2, page 10. This is velocity x dot. This is acceleration x double dot. Remember that? Yes, everybody? Now if I apply the Laplace transform by assuming that the x at time 0 is velocity at time 0 and the acceleration at time 0 is 0 at time 0. If you apply Laplace, what you're gonna see? X of s, now you know it. One time derivative will give the s x of s. Another time derivative gonna be s squared x of s. In analogy, this is your position. A derivative give you s g of s. See? And acceleration gonna be s squared g of s. That's why we name it position. In analogy, a very simple analogy. Okay? And velocity and acceleration. Everyone got it? Yes? Huh? Good. Now let me finish the topic, because you have to combine both topics I taught today. Case A. When you have ESS is 1 over 1 plus Kp. 1 plus Kp. What was the Kp? Was 1 plus G0. Now I'm going to say, if your system type is 0, that's right, means your G is like this. J from 1 to M T, I'm sorry, I said IS plus 1, J from 1 to N T prime JS plus 1. See what I'm saying? So if that the case is, your type is 0 for a static position. So G at 0, I'm going to put in here, G at 0, S is 0. This is gonna be 0, this is gonna be 0. 1 by 1 by 1 by 1 is 1. 1 by 1 by 1 by 1 is 1. So the remaining is k. Here we go. Okay? So you get that. Oh, let me delete that. Because I want to make a table. So you get that ESS, steady state error signal, for type 0 system, gonna be 1 over 1 plus k. 1 plus k. A constant error signal you're gonna have. Remember, in this case, the input was unit step. Unit step. Now case 12a, case 2. Let me change the color. 2. If the type of the system is 1 or n is 1. So ESS, okay, when n is 1, you're going to have one S here, guys. One S here. ESS is going to be, okay, let me first calculate G. Your G at 0, here, KP. This is KP. This is 0, 0, 1, 1. K divided by 0 is how much? K divided by 0? How much is that? K divided by 0? K divided by 0. Infinity. Right? Huh? You get it? Yes? So 1 divided by infinity, hmm? One divided by infinity. I'm sorry, this is ESS. ESS. How much is that? Because this is infinity. 1 divided is 0. Here we go. Okay, if type of the system is 1. Okay, we got it. So it says with the unit step, if you had one integrator, error signal goes to 0. As I taught you, now it corresponds. 1 over S is in I. I is to remove the error signal. Error signal goes to 0. You see what I'm doing, everybody? Huh? Now, 3. If type of the system is 2, type of the system is 2, or n is 2, means your G is this, k over S square pi, I'm just writing terms, S plus 1 from I from to M, I, J from 1 to N, T prime JS plus 1. Again, your G at 0 gonna be infinity, and the ESS gonna be 1 divided by infinity, 0. So I can now make a simple table here. I'm gonna add them later, okay? Type 1, or let me write like this. Type 1, n is 0. Type 0, n is 0. Type 1 and type 2. And we are talking about the steady state error signal. Okay? You got it? So ESS gonna be at time with the unit step as input, gonna be infinity, 0, 0. ESS gonna be 0. See that by adding integrator, I'm writing here, by adding integrator, steady state error signal goes to 0. You are adding integrator here. I. That's right. Now let's go to case 2. Case 2 was ESS was 1 over KV. That's right, KV. Remember, KV was SG0. And our input to the system was ramp for this. Okay, let's now analyze again. Case 1. If type of the system is 0. If type of the system is 0, so S G of 0 gonna be this, guys. S K this TS plus 1. I'm dropping the indices, okay? Pi TS plus 1. I'm gonna put that IJ. So SG0 gonna be this, okay? You got it? Huh? This, guys. So how much gonna be this? How much gonna be this? This is gonna be 0, that's right. S is 0. So ESS gonna be 1 over 0, gonna be infinity. Oh, you have a large number of that. Large error signal. You have no integrator. Now case 2. B. Can you please mute? Can you please mute? Can you please? Can you please mute? 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 So type 1, N is 1. So SGS, which is KV, gonna be, because type 1 gonna be S K pi TIS plus 1 divided this pi multiplication TJS plus 1, and type is 1. You have S here. Here we go. S with the S goes, and you get again K. So ESS gonna be 1 over K. Good. From large number of error signal, by adding a controller, I controller, you take it down to a constant bounded error signal. When I say N is 1, it means you add one integrator, I controller. I controller. And the C, when it N is 2, type 2. So your KV, which is S G of S, K pi TIS plus 1 pi TJS plus 1, and it's type 2. Here's what type 1. This is S squared. So you have S here, so it's gonna be 0. 1 over 0 gonna be infinity. So ESS gonna be 1 over infinity, and you made it 0 now. by adding another I controller. See the process? Without any I controller, type 0, you had unbounded error signal. But we added a controller, I controller, you bound it to constant number. We add another I controller, we made the error signal to 0. In the last case, C, when the type of the system was 2. We saw that ESS we derived together was 1 over KA. What was KA? KA was S square G0. We just defined. Case A, when your type of the system, I'm sorry, what did I say? Not type of the system, which is wrong. When ESS is this, okay? So with type of the system is 0, means there's no integrator. So KA gonna be S square K pi Ti plus 1 divided by pi TJS plus 1. Gonna be 0 because of this. That's right, KA. So ESS gonna be 1 over 0. Oh, unbounded error signal is not good. I'm talking about any system, any order. Okay, I'm talking generally. Case B. Case 2. When you add the integrator, type 1 system. So you get KA gonna be what? Let me call this, guys, for simplicity, term A, A over S, add integrated. Again, gonna be 0 because, see this, S. So ESS again is 1 over 0 infinity. Oh, you still have, even by adding one bounded, right? One bounded, by adding one integrator, you have unbounded error signal. So let me add another integrator. N is 2, type 2 system. So now KA gonna be S square in A by 2 integrator. Now it's gonna be K, this K. Now the error signal, you made it bounded. So ESS gonna be 1 over K. See? 1 over K. Now I can make complete table. By type 0 system, type 1 system, type 2 system. When I applied the unit step as input to the system, and this E was 1 over 1 KP, the error signal, we are talking about the error signal. With no integrator was, I don't remember it, was infinity, no, what was the table? Yeah, infinity 0, 0. Infinity added integrator 0, 0 for unit step. Okay. Then for parabolic input, ESS was 1 over KV. Here was infinity 1 over K and 0. 1 over K and 0. Guys, this is right? This is 0. Oh, yes, this is 1 over 1 plus. Why I did this is wrong here, guys? Why I said here 1 over 1 plus k. I see that something is wrong. I remember it from previous year. 1 plus k. We derived it together. See, for case a type 0. So here is let me change the color because this has meaning. 1 plus k, and then type 2 added so 0 and 0. Yeah, this is good. So then we had the parabolic input, and the ESS was 1 over Ka. With no integrator was infinity, and the last, it was 1 over K. Okay, this is the table of system type versus different inputs. It's infinity, 1 over K. Yeah. You got it, everybody? You see, by adding integrator, this direction shows adding integrator. This is N0, no integrator, 1 integrator, 2 integrator. For unit step, we have a bounded error signal. By adding one integrator, 0, 0. For the ramp input, with no integrator, it's infinity. N1 is 1 over K, 1 integrator, and finally 0. Good. For parabolic input, no integrator, infinity, 1 integrator, infinity, and finally N is 2. 2 is 1 over K, bounded error signal. Constant. Now you know everything in the hand. 2, I teach you Roth, Hurwitz, stability criteria. Roth stability. Roth Hurwitz stability criteria. Simply saying, I want to just hint to that. Suppose you have a closed loop transfer function of this s squared plus k1 s cubed plus k2 s squared, this one, plus 2 plus k3. You have a system, fourth order system. This fourth order system can be that 2 mass spring damper I showed to you and we derived in MATLAB and Simulink. But we are not certain how to design spring and damper parameters to make us a stable system. So Roth stability criteria are gonna help us that we find the range of stability of these parameters to make your system stable. And based on this, I'm gonna teach you after the midterm how to design PID controller. Okay? Based on the Roth stability criteria, I'm gonna teach you. The next week, I'm gonna finish this. I'm gonna give you a hint of what's gonna be in the midterm. Then after the break, we're gonna go to PID controller. But